Bismillahirrahmanirrahim. Assalamu alaikum and welcome to our online module. This is the chapter amplitude modulations and the demodulations. And the course title is EEE 351 or 352 Analog or Principles of Communication Systems. Here I am Dr. Ishan Kalim from EC Department CUIWA campus. Okay, let's discuss the lecture contents which we'll try to cover in this video. So first of all, we will cover modulator types. There are a number of modulator types: multiplier modulators, nonlinear modulators, switching modulators, and further how to obtain this switching operation. We will discuss diode bridge modulator and the ring modulator. So what are the multiplier modulators? First, before going into the detail of the multiplier modulator, why we are going to discuss these types of modulator? This is very much important. The reason is that uh, to obtain the signal mt cos omega ct, which we obtained in the last lectures, we need a hardware circuitry. So these types of which kind of circuitry will be used? This can be developed by using these types of modulators. So first of all, we have a multiplier modulators. So multiplier modulators modulation is achieved directly by multiplying mt by cos omega ct. Here we directly multiply. For example, we have a mt signal, message signal, and we have a cos omega ct as a carrier signal. So we just multiply these two signals to use to get the modulated signal. What is the modulated signal? Mt cos omega ct. So there is a problem in this multiplier modulator. What kind of problem? It is difficult to maintain a linearity in this kind of amplifier. So this is one of the main problems which we try to avoid uh, using multiplier modulator, and they tend to be rather expensive. So this process can be expensive. So it is best to avoid them if possible. So how these modulator works? Such a multiplier may be obtained from a variable gain amplifier. So you studied this in detail in electronics course. So how variable gain amplifier works? So in which the gain parameter, for example, the gain is the B of a transistor, is controlled by one of the signals. In this case, we have a massive signal. So it means that the gain of a transistor B is controlled by our massive signal. In this way, when the signal cos omega ct is applied at the input of this amplifier, the output is proportional to mt cos omega ct. So by using a variable gain amplifier, we generated the modulated signal. But previously these multiplier modulators was not recommended, but because the multiplication of two signals over a dynamic range was a challenge for a circuit designer. But due to the advancement in technology, we have a semiconductor technologies nowadays, signal multiplication is not a big challenge. So these types of circuits can be adopted as well. Now let's move to the next type of modulators. This is called the nonlinear modulator. This next type is the nonlinear modulator. Why it is called nonlinear? Because we have a nonlinear functions, or you can say nonlinear elements here. This is one nonlinear element, this is another nonlinear element. So that's why it is called a nonlinear modulator. So before going to discuss this circuit, first of all we should know what would be the desired output of this circuit and why we are going to work on this circuit. For example, we want to obtain the modulated signal mt cos omega ct. This modulated signal we is called the double sideband suppressed carrier signal, as we studied in the last lecture. So mt cos omega ct. To obtain this, we use a non-linear modulator. So how this works? Let's go into the detail. Modulation is achieved by using a non-linear device, such as semiconductor diode or a transistor. It means that this NL is either a semiconductor diode or a transistor. Inside that block, we would have a semiconductor diode or a transistor installed. So The figure shows one possible scheme which uses two identical non-linear elements shown by boxes marked as I already discussed. And for any non-linear device, for example, diode or transistor, how we can represent it mathematically? Let's see that. Input-output characteristics of either of the nonlinear elements can be approximated by a power series. For example, if you have an input x1t and you pass this signal to the nonlinear diode or transistor, then output would be y1t. So how it looks like? For example, yt equals to axt plus bxt. It means when you pass the signal axt xt to this nonlinear device, you will get the output which will be shaped like this axt plus bxt, where xt and yt are the input and the output of nonlinear device. Let's discuss this in more detail how it works. Okay, so let's go into the more details how nonlinear modulator works. For example, if you can see here, this is a function called z of t. So z of t, you can see it's the difference of y1 of t and y2 of t. So we can mathematically write it as a y1 of t minus y2 of t. Whereas y1 of t is obtained as using x1 of t. So what is x1 of t? So it is in the last slide we have seen that it is a y1 of t is obtained as uh, using a power series. So y1t is equal to ax1t plus bx1 square t, as we saw in the last slide. So similarly, y2t is ax2t plus bx2t square. So substituting the two inputs, for example, x1t is cos omega ct plus mt. How we get this? For example, you can see there x1t is equal to mt, and there is another branch coming here. So mt plus cos, after passing through the adder, we will get x1t equals to mt cos omega ct. Similarly, x2t would be mt here, okay, and then there is a minus sign. So mt and cos omega ct minus mt. So x2t will be equal to cos omega ct minus mt. Now after let a equals to be, let this portion is a and this portion is b. Okay, so we let it as this after putting the values. For example, x1t and x2t we put in this equation. So a equals to a cos omega ct plus mt plus b cos omega ct plus mt whole square. You can see this. We put the value of x1 here and x1 here. What is the x1? Cos omega ct plus mt. Similarly, so after solving this, we called it a cos omega ct plus this, and you know that cos omega ct plus mt is equal to cos square plus m square t plus 2b cos square cos t plus into mt. Similarly, for the b ax2 dx2, what is the value of x2? It is cos omega ct minus mt. So we will put in this equation. So after opening this, a cos omega ct minus mt plus b cos omega ct minus mt whole square. So after opening this, we will get a cos omega ct minus amt plus b cos omega ct omega square ct plus b m square ct minus 2b cos omega ct into mt. So there is a negative sign here. This is a negative sign here. So after subtracting a minus b, these two terms will be cancelled out. A into this will be cancelled out, and similarly this term cos omega ct and this cos square omega ct will be cancelled out, and similarly b m square t cancel out and b m square t will be cancelled out. So what two terms remained here? So we have a AMT and similarly minus AMT. So AMT minus into this minus will become plus. So 2 AMT and these two become plus. Similarly, 4b mt cos omega ct. So this is the z of t we obtained here. So what is the value of z of t? 2amt plus 4b mt cos omega ct. Now it is in your information that for the modulated signal, what we need to obtain mt cos omega ct. This is our modulated signal. So to obtain this one, we will pass it to the band pass filter tuned at omega ct. So after passing to band pass filter, these terms will be ignored or removed. So we will left with the only live with only 4b mt cos omega ct, which is our desired output. You can clearly notice from this that we have a 2amt plus 4bmt cos omega ct. After passing to this, we have 4bmt cos omega ct. This is again showing that after passing through the filter, what would be the result? For example, ZT is passed through a band pass filter tuned to omega c. The signal AMT is suppressed. This part, it means this part would be suppressed out, and the desired modulated signal 4bm cos omega ct passed through, and we would have this final output. Note that the carrier signal does not appear at the input of the final band pass filter. What does it mean? You can see that ZT, this is the input of the band pass filter. They are mentioning here that carrier signal does not appear. What does it mean? You can see from here ZT is equal to 2amt plus 4bmt cos omega ct. You are not seeing any kind of independent carrier signal here. It means that no independent or the separate carrier signal arrive in the ZT. But you can see that the separate message signal is here, but separate cos omega ct function you are not seeing here. Cos omega ct is not here. So as cos omega ct does not appear in this Z of t equation, so this circuit acts as a balanced bridge for one of the inputs. So when the input doesn't appear at the outputs, so it is called a balanced bridge. But here it is called for the one of the input it is called balance, which is called the carrier, because here the carrier doesn't appear at the input of the band pass filter. So it is called a single balanced modulator. You understand now why it is called a single balanced modulator? Because at the input, it means at ZT there is no independent cos omega ct, but we have m of t here. So it is called a single. If we don't have this term, for example, we don't have a mt here and we don't have a cos omega ct here and only this term here, so then it would be called a double balanced modulator, right? So this was the explanation of how nonlinear modulator works, and by passing by giving empty cos omega ct two types of inputs. Finally, after passing through these stages, we get the modulated signal empty cos omega ct. But you should remember this is double sideband suppressed carrier AM modulated signal, because in this modulated signal we don't have any independent carrier signal, but only the modulated signal empty cos omega ct. Let's discuss another type of modulator, which is called a switching modulator. Right? As it can be clearly noticed from its name, that switching modulator, there is a term switching. So you would have learned these concepts of switching in electronics many times, because what does it mean? That switching usually you use for switching a diode. So if you use a diode, for example diode, then when you pass a signal from the diode, you will get either positive side and the negative side will be the clipped off. So this is called a simple switching operation. So these types of switching process can be used to generate the modulated signal. How it is used to generate the signal? Let's go into the detail. Switching modulator. The multiplication operation can be replaced by a simpler switching operation. In the last modulator, we did the multiplication, which is a complex process. So to here we will replace the switching. multiplication operation by a switching operation. So how it works? The modulator signal can be obtained by multiplying MT not only by a pure sinusoid but any periodic phi t of the fundamental radiant frequency omega c. What does that mean? That you have a multiplier, you want to modulate this massive signal m of t, right? This is your modulating signal. So usually we multiply with a carrier which is a pure sinusoid. What does it mean? Like in the last get we use cos omega ct, which is a pure sinusoid. So instead of generating a pure sinusoid, we will generate the similar carrier by using any periodic signal which has a fundamental frequency omega c. How it works? Let's see. Such a periodic signal can be expressed by trigonometric Fourier series, as we uh, studied in the previous lectures, that any periodic signal can be represented by a Fourier series. So what kind of representation is that? For example, uh, we can represent any signal in terms of sine or cosine terms. For example, Cn cos n omega ct plus theta n. This is called the trigonometric Fourier series. So using this and by finding these coefficients, we can represent any type of periodic signal in terms of a sine or cosine terms. So this is phi t we will obtain. So in the end, we will multiply this phi t with the mt. So we will get mt. This can be our carrier phi t, but it's not a sine cosine. It can be any periodic signal. So finally, we would have a representation like this: C n mt cos omega n omega ct plus theta n. And this shows that the spectrum of the product, for example, spectrum means the frequency of the product mt cos omega t is the spectrum mx shifted to. It means that the spectrum is shifted to the frequency plus minus fc plus minus 2fc and plus minus nfc. It means there are n number of terms generated after multiplying the message with the periodic signal. So if the signal is passed through a band pass filter of a bandwidth 2 Hz and tuned to fc, we get the desired modulator signal. What does it mean? As you can notice that after multiplying mt with the phi t, we would have the n number of terms plus fc plus 2fc plus nfc. But our desired target is to obtain only the fc term, right? Fc, because you can see here mt cos omega ct or fc. So we only need one frequency. So after passing this to a band pass filter, which is tuned to the bandwidth of 2 Hz, we will get the desired modulated signal C1 mt cos omega ct plus theta 1. And don't worry about this theta 1. This can be any starting point of the phase. So it can be 0 or any value. So let's see it pictorially. For example, this figure 4.4 switching modulator for double sideband suppressor. This is our massive signal, and in the time domain, similarly, we can write it in a frequency domain as m of l. Show it as in a frequency domain. So this would be our WT. WT, like generated any periodic wave, which we generated last slide. So it can be any periodic wave. So it can be represented as the pulses or something like that. So after multiplying mt with omega t, we can obtain this mt or omega t. And if we represent it in the frequency domain, we would have a 0 fc minus fc and the number of terms. But after passing through the band pass filter, we would obtain only the 2 pi mt cos omega ct. So it means that there would be a number of terms fc minus fc plus 2fc minus 2fc, but as we pass through the band pass filter, we will only get the 2 over pi mt cos omega ct, which is the desired modulator signal. So let's read it. The square pulse train in figure 4.4b, this is 4.4b, this is a square pulse train, is a periodic signal whose Fourier series was found earlier in example. In chapter 2, in example 2.8, we already found the Fourier series of this periodic pulse trains. square plus t. So what was that? Omega t is equal to 1 by 2 plus 2 pi 2 over pi cos omega c minus 1 by 3 cos 3 omega ct and so on. So the signal mt omega t is given by mtw. So just we multiply mt with this wt. So what we would achieve, mt half mt plus 2 over pi mt cos omega c, just multiplication of this. So in the next slide, let's see how we separate this the desired signal. The signal mt cos consists of infinite number of modulated signals, as we have discussed in the last slide. FC, 3FC, 5FC, there can be n number of modulated frequency signals. Okay, so spectrum of mt omega t consists of the spectrum MF and MF shifted to the FC plus minus FC, 3FC, so on. But we are interested only in mt cos omega ct. To separate this, we pass mt to a band pass filter of 2 GHz centered at plus minus FC. So look at this. This was the plane signal mt cos mt omega t. So after passing through the band pass filter, this is band pass filter, we will obtain 2 by pi mt cos omega ct. This is the desired signal which we want by ignoring the higher frequency terms. Okay, in the last slides we have seen that Wt is a square wave frame. So how to generate this square wave, we need a switching operation. For switching, we will use here a diode bridge modulator as a switch. So diode bridge modulator will act as a switch here. How it works? There are 4 diodes, D1, D2, D3 and D4. Here D1 and D2 are matched pairs. What does it mean by matched pairs? In simple terms, we can say that their properties are same, right? And for further details, you can refer an electronics course or class. And similarly, D3 and D4, D3 and D4 are matched pairs. It means their characteristics are almost similar. So how it operates, like how it generates the square wave frame. Look at this. This is a cos omega ct. This is a AC voltage supply which we provide to the this base circuit. So when C is positive, like in the first step, when C is positive and D is a negative, so what will happen? The D1 and D2 diodes will conduct, and similarly D3 and D4 diodes will conduct as well. So both of them, all of them will conduct, and since the D1 and D2 and D3 and D4 are matched pairs, so what will happen? There will be similar voltage at the terminal A and terminal B, which we can say that they will effectively add as a work as a short circuit. So it means that this switch is closed, right? So what happens in the next cycle when this terminal becomes negative and this becomes positive? All of them will not conduct, like all of 4 diodes will open, and it will result in the opening the terminals A and B. It means the connection between A and B, there will be no connection between the A and B. For example, this one, there will be open circuit, right? So uh, this was the way to generate the pulse like this one, right? So on on off, right? So this will be a on off pulse. So it means that from this circuit A and B, we will just obtain WT, right? This is diode bridge circuit. Our modulator is to obtain W of T, nothing more. So in this slide, we will see that how the role of the electronic switch, which we discussed diode bridge in the last slide. For example, the diode bridge serve as a desired electronic switch. As we mentioned, this only the purpose of this switch is to just turn on and off, right? Where terminals A and B open and close periodically with the carrier frequency omega fc and when a sinusoid is applied across the terminal CD. When we apply a sinusoid here, this is A cos omega CD, across the terminal CD, it results in opening or closing the terminal A and the terminal B. So if we want to use this switch in the circuit like the series bridge diode modulator, this is a modulator circuit. What we do, this is our message signal which we like to modulate, and this is our band pass filter, and in the end we would like to obtain KMT cos omega CT. This is our desired target. So in between A and B, what we do, we put this circuit here, right? A and B. These are the terminal A and this is B. So when there is a positive at the C, like the C is positive, like C is positive and the D is negative, what will happen? This will act as a closed circuit. So MT will pass here, and after multiplying with the omega T here, WT here, so there will be frequencies, number of frequencies and number of frequencies. So we need a band pass filter, as we already discussed, to filter out the desired frequency omega CT. So in the end we will obtain the modulated signal MT cos omega CT. So when C is negative and D is positive, what would happen? There will be no circuit here. It will act as an open, and no conduction, and there will be no result. So this was the series bridge circuit. Similarly, if we would like to use a shunt bridge diode modulator, so in that case we will place this in a parallel. So this is called a shunt. So the circuit operation will be inverse as compared to the series bridge modulator. How? When the C is positive and the D is negative, so it will not conduct, right? It will not conduct, and because it will just become short and the current will start flowing here. And while when C is negative and D is positive, it will conduct and we will get the desired output. So this was the one of the example of the switch which we studied here, was a diode bridge modulator. The other type to obtain this switching operation is the ring modulator. This is your reading assignment. Please study the book and try to understand its working procedure. I would like to thank you for listening this lecture, and for question answer there will be a separate session that the date and the time of the session will be communicated later on. Thank you.